So now I want to define Anosov subgroups. So recall this subgroup minimal, this minimal parabolic subgroup, P equals MAN. And here M is the centralizer of A inside K. We have this Furstenberg boundary that we saw in Kant's talk, G mod P. And so this can be described as the space of complete flags. And we'll use the notation F to the 2 in brackets for the unique open G orbit in F cross F. And this is the pair of complete flags which are in general position. So if I take a line in the first one and then a plane in the second one, then they will add up to R3. Okay, and so the definition that I will use in this talk is that if I take a Zariski dense discrete subgroup gamma, then we will call it P Anosov, but from now on I will drop the P and just call it Anosov if it is a finitely generated word hyperbolic group which admits this boundary map from the Gromov boundary to the Furstenberg boundary. And it is such that it has this antipodal property. If x is not equal to y, then if I push the x and y into the Furstenberg boundary, then they will be in this unique open G orbit. Okay, now I want to get into the statement of the results, but I need a little bit more background before that. So recall this Cartan projection, mu. So in Kant changed it to kappa, but yeah, I like I'm used to mu. And then we have this Jordan projection. So if I take an element G, as we saw, we can decompose it into the elliptic, hyperbolic, and unipotent components, and the hyperbolic part conjugates into A sub something, and then that something is lambda G, and this will be in the Weil chamber. And so by the work of Benoit, we have these two important objects. We have the limit set and the limit cone. The limit set is, we can describe it as the unique gamma minimal set inside the Furstenberg boundary. And so this turns out to be the image of the Gromov boundary by this boundary map. And the limit cone is, we can describe it as the smallest closed cone containing these Jordan projections. And this will be a convex cone. And so just a couple more things. So we started seeing today this growth indicator function. So we can define it as follows. Take a point V in the Lie algebra of A. Then this function will be homogeneous in the radial directions. And along each radial direction, we can take the infimum of this quantity here, tau sub c, where c is where tau sub c is this kind of the abscissa of convergence of this series, so it's analogous to a Poincare series, and yeah, so we can define this function, and this is, as we've seen, this is concave and positive on the limit cone. And when gamma is Anosov, then we have some more properties. So this is due to Sambarino. So in the Anosov case, we also know that this growth indicator function is analytic and strictly concave. And this is, as mentioned briefly, this is, you show this using the power of thermodynamic formalism, because you can relate this to certain maps involving the pressure functional, and these maps will be analytic, and so from there you can kind of deduce analyticity. And because of the analytic property, we can get a one-to-one correspondence between a direction and a functional. Or sorry, more specifically, a direction and a functional which is tangent to the growth indicator function along V. So if I pick a V, there's a unique functional which is tangent along V. Okay, now before getting into the results, I need to address a subtle point, which is that the group M is not necessarily connected. In the rank 1 case, it's connected, but in higher rank, this is not necessarily true. So how do we deal with that? Well, so the issue is if you flow along ATV, then you would like it to see the whole non-wandering set. The non-wandering set is omega, such that so omega is defined as gamma g, so a point in G mod gamma, so that G plus minus is in the limit set. Okay, I didn't define G plus minus, so G plus is GP, which will be inside G mod P. And so you want G plus to be in the limit set, which means GP, which goes into, which is a point in the Furstenberg boundary, you want it to be in the limit set, and G minus is something similar. It's a G times W 0 times P, where W0 conjugating elements in A by W0 corresponds to this involution on the Weyl chamber. So you want both G plus minus to be in the limit set. So this is analogous in the rank 1 case, where you take the forward and backward endpoints. And so this omega is the non-wandering set, and you would like the flow to see all of that, but this might not be possible because M is not necessarily connected. So what one has to resort to is looking at the P0 minimal subset, where P0 is the connected component of P. So this is the same as the connected component of M times AN. And then you look at the stabilizer of this set inside M. And this will give you a subgroup M sub gamma. And this will be a finite index subgroup of M. And so the natural kind of replacement is you would like to see everywhere inside omega sort of associated to this M gamma. And so what you have to do is decompose omega into a disjoint union omega sub M, where M goes through this finite group M mod M gamma. So this actually comes up in Dang's work already when she studies topological mixing. And by result of Minju Lee and Hyo, these are also the A-ergodic components of the BMS measure. So I didn't define the BMS measure yet, but yeah, it turns out they're the A-ergodic components. Okay, so now before going into the main theorem, I want to give an appetizer. So most people are usually more familiar with the Haar measure or find it more interesting. So I'm showing this application first. And so this is a theorem due to Sam Edwards, Minju Lee, and Hyo. So in the first iteration, I want you to ignore the purple parts. So this theorem says that if you take V inside the interior of the limit cone, then there's a constant kappa V, a positive constant kappa V, such that if I take test functions phi1, phi2, which are compactly supported functions on G mod gamma, then I have the following. So what does it say? You take this correlation function, phi1 of x ATV, you move by this flow, ATV. Then you multiply with phi2 of x, and you integrate with respect to the Haar measure. So this is also the matrix coefficient of ATV. And if I normalize by this function here, then and if I take the limit, sorry. Yes. Can you make it slightly smaller so everything fits in? Sorry. Can you make it slightly smaller so the Oh, like this? Okay, yeah. Now the whole statement is showing. Right, so you have this correlation function, and I normalize by this function, which is t to the rank minus 1 over 2 times e to the 2 rho minus psi v evaluated at tv. 2 rho is the sum of positive roots, and psi v is this psi that we picked, tangent to the growth indicator function along the direction v. And then if you take a limit, you get this constant times some other constant. But this constant is in terms of phi1 and phi2. You have to, it's the measure of, you integrate phi1 and phi2 with respect to some Borel measure. So these are the Berger-Roblin measures, but I'm not going to define it. And because of this phenomenon that you have these ergodic components of omega, you have to have this sum over these ergodic components. But what's the point? The point is that we know that the matrix coefficients vanish by Howe-Moore, and this theorem is is showing how, in what way this matrix coefficient is going to 0. So we can restate it in an asymptotic way, where you say that the matrix coefficient is decaying as 1 over this quantity here. Okay, now let me. Before I move on, is it clear? Are there any questions? Okay, so now I will explain the purple parts. So the purple part is to basically introduce a perturbation of the flow. Instead of going exactly in the v direction, you want to also perturb and go in a direction transverse to the v direction. So then the theorem says the following: there also exists this special inner product where you just denote by the usual inner product sub star, such that if I take a function r, a positive function with these properties, this is just saying that r of t over t, the limit exists where you allow plus infinity, and we denote the limit of rt squared divided by t as some number L, and we take vector u transverse to the v direction, where you do it by taking a vector in the kernel of psi v. Then the theorem changes in the following way. In this exponential quantity, you have to add this RTU. The flow is now not just, you don't just move by a sub tv, but also by, it's a sub tv plus RTU. Then the limit modifies by this exponential quantity here, which depends on u. So this is e to the minus this constant L comes up here times IU, and IU is this is just the distance of u to the line along V, the distance squared from u to the line along V. With respect to this star inner product. Okay, now I will briefly mention that in rank 1, this reduces to what is already known. So this is due to...
why in the theorem the limit of RT over T does not occur? You assume there is a limit for RT over T. And this limit doesn't occur in the formula?
You're saying why R does not appear?
No, why the limit? You have a limit RT over T, which is, you assume there is a limit of, there's this limit, why?
Yeah, I guess this is just a condition on R, but the quantity does not appear.
The limit doesn't occur.
Yeah. The main quantity is this. In the rank 1 case, we get this statement. This is due to Winter. So you take the correlation function and then you normalize by e to the d minus delta times t. Delta is the critical exponent, and d is the volume entropy. In the real hyperbolic case, this is just the dimension of the boundary, but in the other cases, because you have twice the simple root, you have to modify the growth of volume according to that. So this is some other quantity d. So this is just to compare with the rank 1 case. And so the proof of this, okay.
This limit is 0. It's not a consequence of since the limit of rt square over t is L, then the limit of rt over t is 0. In fact, this limit can be non-zero, or
which one?
He's asking if, because of this condition, RT square divided by T has a limit, so maybe the limit of RT over T is always equal to 0. Isn't it the consequence of the...
No, you're allowed to take, for example, RT equals T.
Then that will be infinity, then it is just 0. So
you accept infinity.
I think the most interesting case is RT is simply square root of T. So that's what you need.
Yeah.
Just think of RT as
But
square root of T.
I allow plus infinity.
you allow plus infinity.
Yeah, I allow plus infinity. And yeah, so the interesting case is RT equals square root of T. Then you get something interesting here. But I think if you take a linear function, that also gives you some information. Because, for example, if you pick a direction v, and then you take, okay, maybe I'll mention this afterwards when I show local mixing. So this is proved by generalizing Roblin's transverse intersection argument, and using the local mixing theorem as input, which I will show below. So now I have to introduce the BMS measure. So Kant constructed these Patterson-Sullivan measures for linear form psi tangent to the growth indicator function. And roughly speaking, this is the weak star limit of this quantity. This is analogous to the rank 1 situation, where you take a weighted sum over Dirac delta masses, except in this case we can, instead of using Dirac delta, because you have issues with how you go to infinity and which boundary you converge to, so we can take a k invariant measure and then move by gamma and take this weighted sum divided by, and then you just normalize. And in this formulation, you take S to 0. And you get a measure on the Furstenberg boundary, and this will be supported on the limit set. And so instead of denoting mu sub psi, I will denote this by mu sub v, because as I said, we have this one-to-one correspondence between the direction and psi for gamma and Anosov. Now using the Hopf parametrization, G mod m is, you can parameterize as this f to the 2 cross the Lie algebra of A. And what you do is you put the PS measure in each factor of the Furstenberg boundary, and then the Lebesgue measure on A. And then, okay, I'm not defining the Boozman function, but there is if you put a right factor, the correct factor in front, then this allows this measure to become left gamma invariant and right A invariant. So this is the important property.
But you might want to emphasize in the second factor. You change the direction by opposition involution.
Yeah, you have to use this opposition involution. Okay, so using this measure, we have this local mixing theorem. So again, first I'll go through it without the purple parts. So you take V in the interior of the limit cone. Then there's this constant kappa V, so that for all these test function, you take the correlation function, but this time with respect to the BMS measure instead of the Haar measure. And then you don't have to include this exponential part. You normalize by t to the r, the rank minus 1 over 2. And if you take the limit, you get constant times these constants in terms of phi 1 and phi 2. So usually what happens is you want this to become independent, and you get the integral of phi 1 and phi 2, but you get this local mixing on each ergodic component. So you don't have to write this sum if you restrict to our ergodic component, but if you just write this in general, then you get a sum over the ergodic components. And then again, if you add the purple parts, then you have this special inner product, and you take a map R with these properties, and then you can perturb the flow in this kernel direction. And if you do that, you get this extra dependence on U by this exponential. So it's decaying as you go further away from your V direction. And so here's the analogous rank 1 description. This normalization disappears in the rank 1 case, and you have the usual mixing statement with respect to the BMS measure. So the thing I was mentioning before is that if suppose you pick a direction V, then you have this BMS measure with respect to this direction V, but maybe you want to look at the behavior if you flow along a different direction, say W. Well, this map R helps you do that, because you can take a linear R, then this flow will be along a different direction W, and it shows that this factor is showing that it will go to 0, because L will be plus infinity in that case. Okay, so we didn't get this out of thin air. There are many important works before this. So the first one I want to mention is Therian. So he first proved this for not just Schottky groups, but ping pong groups, by which I mean you allow cusps. And where the flow is along the maximal growth direction, and you take this R map to be the square root of t, and these functions are M invariant, or in other words, these functions live on G mod gamma mod M. So that is a key difference. So in his work, this local mixing result was on G mod gamma mod M instead of the homogeneous space G mod gamma. And Sambarino was the first to put it into this Anosov context. So So in his work, gamma was pi 1 of a closed negatively curved manifold. Then R is this square root of t. And again, it was for test functions on G mod gamma mod M. And Babbio and Winter proved the rank 1 case. Babbio was for the geodesic flow, and Winter for the frame flow. So G mod gamma mod M versus G mod gamma.
For geometrically finite case.
Yeah, for more general than Anosov. But same with Therian, because he also allowed cusps, so that would be called relatively Anosov. And yeah, I also wanted to mention this local mixing is not our terminology. This was coined by Hio and Wanyu Pan in their paper, where they get a mixing statement but with this normalizing factor. Okay, so now I want to discuss some more applications. Oh, I actually forgot to mention something. In this theorem, another important point is that not just this limit, but we can also give a uniform bound for this. So this quantity is actually, if you flow far enough, this quantity is bounded by expression of this form. Some constant, you can put this together with kappa v, it will be bounded uniformly by some constant depending on phi 1 and phi 2 times this exponential, which depends on u. So this purple part is actually very important because this kind of uniform bound is crucial in some counting applications. So the first application I want to mention is topological mixing. So only for this theorem and the next one, gamma is not necessarily Anosov. Gamma is any Zariski dense discrete subgroup of G. And from this local mixing result, you can deduce that if you take a direction in the interior of the limit cone and you pick a ergodic component, and if you flow on G mod gamma, this flow is topologically mixing on each ergodic component. So meaning that if you take two open sets, capital U and capital V, then if I flow U far enough, then for sufficiently large T will always intersect capital V. And the proof is by basically taking, once you pick a direction V, then you can find a Schottky, an appropriate Schottky subgroup in gamma, so that V is contained in the limit cone of that Schottky group. And we know that Schottky group is Anosov, and then you apply the local mixing theorem. So that's essentially how the proof goes. So Dong proved this for the case that the connected component of M is abelian. But with this theorem now you can remove that condition. As far as I can tell, I think this abelian condition comes from something related to the generalized length spectrum, and some density result related to that. I will talk about this later. And she also proved a converse, and the converse is without this abelian assumption. And what do I mean by converse? Well, I mean that you can think of this theorem as saying if V is inside the limit cone, then you get topological mixing. So if you put the converse together with the previous theorem, then you get a nice if and only if statement. So in the same setting above, pick a direction inside the interior of the Weil chamber, then this flow is topologically mixing on any of the ergodic components. It doesn't matter which one, because they're all, the dynamical systems are all isomorphic. So on any ergodic component, it's topologically mixing if and only if V is in the interior of the limit cone. Okay, any questions before I move on? Okay, if not, I will discuss another application. So I didn't mention this before, but this omega, due to this Anosov property, omega has the following structure. This is just a trivial vector bundle. Kernel of psi times some base space fancy x. And this base space will basically turn out to be this Gromov geodesic flow, this space associated to the Gromov geodesic flow. So you have closed geodesics in the space X, and they're in one-to-one correspondence with the conjugacy classes in gamma. And so I have a picture here, and I will define this set fancy C sub psi of T, which is the set of cylinders with psi circumference less than equal to T, meaning that if I pick basically, if I pick a geodesic, maybe I should have written a geodesic here. If I pick a geodesic in X, then there is an associated gamma element in gamma, and okay, it doesn't matter which representative in the conjugacy class you pick. Then you evaluate lambda on gamma, and then we can make it into a real number by evaluating psi. And we want this to be less than equal to T. So take all such cylinders C. And why am I calling this a cylinder? Because in this vector bundle picture, you have a geodesic in this base space. And then if you lift it, then you just get a cylinder. And this is a very recent result by Michael Chow and Elijah Fromm. It's a very recent preprint. And the theorem says the following. If I take a function, compactly supported function on G mod gamma mod M, and a class function on M, then we have the following joint equidistribution result. So you take there's a Lebesgue measure on the cylinder because it's just a quotient of the Lie algebra of A. And so take the integral of f with respect to this Lebesgue measure. This is fine because f is compactly supported. Then evaluate this class function on h sub c. What is h sub c? It's the holonomy associated to this geodesic in the base space. So as you go along this, so you can think of it in the following way: you have gamma, then gamma is conjugate to some element in A times M, and you take the M part. But this is well defined up to conjugacy in M, but that's okay because this is why we're taking a function, a class function. Okay, so you take this quantity, sum over the cylinders with psi circumference up to t. You normalize by 1 over e to the t, and then the limit will give you this constant.
It's not e to the t, it's e to the delta v times t, I think. The normalization, I think, yeah, it's not e to the t, it's entropy times t, right?
But entropy is 1.
But I think because psi is tangent to, I think, the growth because of that, I think. Yeah, so it goes to the constant BMS measure of f times the Haar measure of psi, but restricted to this m gamma, divided by the mass of this base space. Yeah, so I forgot to write this down, but I should mention that there are lots of previous results for rank 1, and if you take the indicator function, and if you forget about the holonomy part, then you get counting results, right? So this is one of the first results is by Margulis and Bowen, and then also for the higher rank situation, you have results by, I believe we mentioned Kant's result for the Schottky case, then Sambarino's result, and then with the holonomy aspect, in the rank 1 case, there are results by Polycott and Sarnak, Wakayama, and also in the rank 1 case, with the holonomy aspect, or with this both this counting aspect and holonomy aspect. This is a result due to Margulis, Mohammadi, and O. And so this result is actually a generalization of that result. Okay, now I will discuss some proof techniques. So this is proof techniques about the local mixing result. So you have to use the fact that omega has this vector bundle structure. I forgot to mention that this is really an observation due to Sambarino. So you have this vector bundle structure. You can apply psi to project to this base space X, which is the limit set, this quantity, limit set to the 2, which is you're taking pair of points which are distinct, times R, and you mod by gamma. So following the works of Bridgman, Canary, Labori, and Sambarino, and also Carvajalis, this action is properly discontinuous and cocompact. And so it makes sense to quotient by gamma. And so this base space is a compact Hausdorff space. And as I mentioned before, this is really just this Gromov geodesic flow. The translation flow on X, by which I mean you translate in the R part, conjugates to a reparametrization of the Gromov geodesic flow. If your gamma is just, for example, a surface group, then it's really just the geodesic flow on the surface. And so from the work of Bridgman, Canary, Labourie, and Sambarino, they showed that you can get a Markov section, and on a related space, it's not exactly this. And so what we do is import this Markov section, and then you get a coding. So to remind you what a Markov section is, you have some submanifold, some pieces of submanifold of this form, where the unstable direction is in this horizontal direction, and the stable direction is this vertical direction. And you have finitely many rectangles, which if you flow them by a certain amount of time, they fill up the whole space. And they have this very important property. If I flow this first rectangle, then it will hit, when it hits the next rectangle, the stable direction goes into the stable part of the next rectangle. So I drew the image of this rectangle using dotted lines here. So you can see that the stable part, which is this, is contained in the stable part of this green rectangle. And the unstable part enlarges and swallows the unstable direction of the green rectangle. And you have a similar property in the backwards direction. And this property allows you to code the points on the rectangle by sequences. And so you get a subshift of finite type, sigma, and there's a standard trick to kind of reduce your formulation to just a one-sided sequence. So I call this sigma plus. And here are the important maps, k and theta. You get maps from this one-sided sequence into A, and this one-sided sequence into M gamma. So what you do is, as you the sequence defines a flow, and then when you come back to your rectangle, then you can see what element in A and M gamma that you acquire. So when I mean come back, I mean in the base space X. So you have, first of all, this vector bundle over X. So you can see how much you move in the A direction. And then that is inside G mod gamma mod M. So then you can lift up again and see what element in M gamma you acquire. So, okay, you have these maps. And the important thing is, over periodic sequences, these give the Jordan projection and holonomy. So as I mentioned, if you take a periodic sequence, this corresponds to a closed geodesic, which corresponds to gamma, element in gamma. So you can write it as conjugate of an element in A of AM. And so the A part gives you this Jordan projection, the M part gives you this holonomy. And a very crucial property that we need to use is that when you put the two together, you get this generalized length spectrum, which I'm writing as lambda AM of gamma. And if you look at the group generated by that, then it is dense in A M sub gamma. So this is, if you ignore the holonomy part, this is a result of Benoit, and Leo generalized this, and yeah, so this is the generalized result, and we use this together with thermodynamic formalism. So over this subshift of finite type, we consider transfer operators which are twisted using this map K and this map theta, which is this holonomy map. But then we also use this representation, irreducible representation mu in this twisting. Okay, so we have transfer operator. This is the explicit formula, but yeah, you don't have to, I guess, see the details. And the important fact is 1 is a maximal simple eigenvalue for L 0, 0, 0, and L sub A comma 0, 0 all have spectral gap. So this is for the classical transfer operator. And the key result in the proof of local mixing is that if you take W and mu non-trivial, then we have the following statement. E to the I theta pi, if it's an eigenvalue of L sub 0 W mu, so you're twisting using W and mu, then theta will be irrational. So you cannot get eigenvalues which are of rational angle. I guess I'm almost out of time. The proof sketch is, there are arguments in thermodynamic formalism which we use. So generalizing some argument of Polycott, you first rule out the dimensions of mu. It has to be, this is a proof by contradiction. You show first that mu has to be one-dimensional, and then this mu part is now just a complex number. And there is another lemma of Polycott which says that if you have an eigenvalue, a complex eigenvalue like this, then in the formula, in the summation formula of the transfer operator, you pick out this imaginary part, and that has to be equal to this eigenvalue. And so what's the contradiction? Very roughly speaking, the right-hand side, if it was a rational angle, the right-hand side will be in a finite set. But the left-hand side, using density of periods, you can get a contradiction. So that's the very rough sketch. And this property is useful because you basically get an analytic map. You can show that this identity minus the transfer operator inverse, this Neumann series is analytic with respect to this vector in the Lie algebra of A. And near the trivial parameter, you have a pole, and you can write the transfer operator like this. And okay, then you have to do some more work. But the main term comes from here, from some analysis and taking care of the pole. And so to deal with the integral over this, you need to expand this eigenvalue kappa. So we get a formula for this expansion, there similar formulas have appeared previously. And then when you do the analysis to take care of that term, and when you take care of this pole, this t to the rank minus 1 over 2 factor naturally comes up. And this r minus 1, this is associated to the dimension of this fiber direction, the kernel of psi. Okay, so I'll end with this. Relevant works in this kind of analysis. The relevant work is by Babio, then Ledrapier-Sarig, Opan, and Therian. So it's a similar kind of analysis as these works. Thank you for your attention.
Questions?
Is there any hope to get some sort of exponential mixing?
Yeah, we looked into that, but I don't think it is true. Yeah.
But you are still hoping to get exponential mixing for the base space, right?
Yeah, for the base space, because the base space, okay, if you think of like surface groups, then you have an analogy.
Okay. So the base space is what you call lambda 2 divided by gamma.
Lambda 2 times r mod gamma. So this Gromov geodesic flow.
Yeah, the unitary bundle of gamma.
Yeah.
Okay, other questions? Okay, let's thank Pratyush for an interesting talk.